And that is what startups represent. I am now looking forward to an exciting startup from the EMO startup area. And I would like to welcome the CEO and founder of Metubiq. And he will talk about sub-nanometer precision in inline surface topography measurement under industrial conditions. And to me, this is a very new topic, which is why I'm especially excited for this presentation. And for you, this means that you can ask your questions that I can ask him later on. Please use Slido for that, and I will now pass the floor to him. The floor is yours. All right. Good morning, everybody. Thank you very much for the nice introduction. As already mentioned, I'm Tussin Serbis. I'm the founder and associate and managing director of the still forming company of Metubiq. We come from the University of Kassel, and we have brought a product to the market that for the past 10 to 15 years has been researched on at the University of Kassel for measurement technology purposes. Before I go into more detail, I would like to mention one thing. What is the problem we're tackling here, and what are the challenges we're facing? The integration of optical precision measurement technology for surface topography measurements, unfortunately, we're not able to integrate them into manufacturing processes, and that is because vibrations dominate these processes, and ultra-precision measurement devices are very sensitive when it comes to surrounding vibrations. Now here you can see the result of a pre-measurement process from the lab, a very classical sinus standard that we measured that is used for calibrating machines on the left-hand side. You can see a normal measurement result from a lab surrounding without problems from the surrounding, and on the right, that's the result if there are vibrations around. We're talking a vibration range of 10 Hertz and 200 nanometers in amplitude, and with that you can see the sensitivity of these systems. Right. Currently, all of that leads to quality assurance of ultra-precision measurement technologies can only be done post-production. And it also needs to be done in specially designed measurement labs. During the production, the measurement part needs to be taken out of the machine, out of the production surroundings. It needs to be taken to the specific isolated labs manually, and those are the processes that are very inefficient, and they often lead to a quality assurance that is less than 100%. And that, of course, leads to a very high scrap rate in turn. Now, this is our solution. We enable inline quality assurance, 100% quality assurance of work pieces for high-end precision tools that can be done inline or, in best case, in situ on the machine, and it is vibration immune. Now, what are the key benefits here? Before I talk about the technology itself, this process leads to an early error detection, and that contributes to a closed-loop feedback, and deviations can be corrected. So waste can not only be avoided, but it can be proactively prevented. Because of the closed-loop process control, we also simplify the measurement of parameters of a machine during the process, but also the post-process measurements in an adaptive and proactive way. And those are the benefits that lead to a significant cost reduction, which in turn contributes to the production surrounding being a lot more capable for Industry 4.0. It is safer and it is more stable. Now, in order to understand the initial problem, we use white light geometry. Most of you will know that it is widely established in the industry. It is used to qualify ultra-precision surfaces into the nanometer range. This is a standard CSI basic setup. Without going into too much detail, I would like to explain to you where the sensitivity to vibration comes from in order to make you understand how we correct that. The measurement process consists of a deep depth scan. So the measurement object is moved towards the measurement technology, and in this linear process, a camera captures images that are, in the best case, very regularly taken. From that, we develop a scan from the stack of images, and best case, the result looks like this. These signals come in a curve shape. Now, should this linear high precision process is then interfered with through vibrations, the image stack looks like this. It is irregular. It is not regularly distributed, and that in turn leads to a signal that is very irregular as well. We have strong deviations to the top and bottom, very irregular deviations to the top and bottom. Right. The problem is generally known. Most optimal precision measurement technologies suffer from this. And in the past, there have been several approaches to avoid this problem or even work around this problem. Currently, we have the solution that I earlier presented. We take the measurement process to a specific lab and take it away from the manufacturing surroundings. There are software approaches to this problem, and these approaches use a low-frequency camera image stack, and they sort of calculate they get the deviations out by calculation. It is ineffective, that's what our clients say. Then there are a few manufacturers of commercial products who use high-speed measurement technologies. The approach here is if the measurement speed is going up, the vibrations have less impact and less time to impact the measurement results, and that is the result is an insensitivity towards vibration again. The two next methods, that's active compensation and passive compensation, both use a dedicated additional vibration measurement sensor technology, and during the process, during the in-depth scan, they try to assess the data in real time, and they react with counter vibrations. This mostly doesn't work because there are high latency times that lead to even higher vibrations, and the vibration amplitudes are too high for this to actually work. Now, in between, there are single-shot systems that I've separated from the upper two groups. All of the systems that I've listed on the top, they use the white light processes, and the single-shot measurement technology uses an alternative method that comes with many disadvantages compared to the white light technology. What we use is passive compensation. That means that we come up with a dedicated measurement technology. We measure the vibrations and correct them after the measurement has taken place. Right. The entire process can be divided into 4 sub-steps. Let's start with a dedicated additional vibration measurement. This is the measurement routine. Over the past 10 years, we came up with a patented solution at the university. In addition to our white light sensor, we have a distance sensor that is integrated here, and it does simultaneous measurements simultaneous to the white light sensor. In order to do so, we need the synchronization, the simultaneous measurement, and therefore we have a lot of new hardware in here. We came up with new software in order to make the 2 systems act as one and act as an individual system. Now, in the second step, first the data from the vibration measurement are assessed, are analyzed. This is the measurement signal of an in-depth scan of 10 micrometers. During the measurement process, we hit the machining table with a fist, actually, and here you can see the results, these blips in the middle. And these additional information makes us able, after the process, to take our faulty measurement data, correct them, and get the right measurement data that we need. And in our third step, we don't have to advertise new technology to our client, because at the end of the day, we get the same signal that conventional technologies would give us, and then we make use of certain algorithms in order to correct the signals and come up with beautiful measurement data. Now, 4 to 5 years ago, we used the measurement technology for the first time outside of a laboratory, and we took it to a mechanical workshop of the University of Kassel. And here you can beautifully see our interferometer in the middle. It is on a table. There is no passive compensational measurement technologies, and we don't use any active compensational methods. We were in direct closeness to a milling machine, and the colleagues of the mechanical workshop there were ordered to make milling processes that are as rough as possible, with more than 10 millimeters. They milled the metal, 10 measurements we did after each other, and you can see that there was a lot of work done. It was rough work, a lot of cuttings around. Right, that's the resulting measurements. On the left-hand side, you see the surveyed in-depth scan, the vibrational amplitudes went up, the milling head went into the metal. That's where you have the deviations here, and then we had constantly high vibrational amplitudes up to 2.45 micrometers. And I also brought here the maximum frequency in the bottom left. It is a multi-frequent signal with frequency of up to 50 Hertz. At the same time, we measured a rectangular nominal height. That is a standard. We had a nominal height of 90 nanometers. And as you can also clearly see here, our system is able to measure these structures and correct the measurements with any circumstances previously, really. But what is a lot more important than the actual pictures is, of course, the repeatability of these sensors. And at this point, we measured with a roughness normal, a roughness standard, and we used a Halle precision normal for calibrating measurements. And from 5 following measurement results, we calculated the standard deviations. This is the result. Here you can see very well that under these optimal laboratory surroundings, we measured the same things as they would usually do without the optimal conditions, and the compensation principle is independent of the vibration frequency. Of course, we had multi-frequent signals that we also checked, so-called vibration sources that were very heavy, and we made sure we had them by hitting the table with our fist heavily. The measurement system works and comes up with repeatability under different measurement preconditions, and this is nothing new. Any conventional white light interferometer gets these values under isolated lab conditions. But with our motto, measure everywhere, and we live up to that motto because we can provide these measurement data in the shop floor. Now, what's also important here is that there were strong vibrations. We used a hammer here to hit the table. That is a situation that hopefully never happens in any workshop, in any production site. And with our potential clients, we always communicate that if you have signals like this, you should check your machine. Right, what you can see here is a depth scan of a measurement range of 10 micrometers, and the vibrations were 3 to 4 times higher than they usually would be. That is the limitation. We set a laser interferometer that has a limited measurement range. 2 measurement points can only be 2 nanometers apart from each other. Here, at the height of the vibration signal, we can see that with signals like these, 2 points are only differ in 100 to 150 nanometers, and that is because of the measurement technology we use. It comes with a resolution of 160 kilohertz, and that is why it can scan the probe very quickly. Now, through this, we can make sure that our measurement systems are vibration immune for any surroundings, and they are reliable, and they can feed the measurements back into the software. We have a software that makes sure if the measurement technology is interfered by anything, we can survey, we can monitor that. We see that immediately. The distance and vibration measurement is what we then start earlier and end later, and that has to be our scan range. If that's not the case, our vibration scan measurement technology knows that something went wrong, and the measurement result would then be thrown away and done again. Now, last but not least, I would like to highlight that all of this can be done without actual expertise on the topic, because between the measurement data, there's always a magical line that makes sure that the measurement results, in this case, are secure and can be fed back. Otherwise, a measurement technology expert would have to always monitor the results, and in this case, they don't. Now, I need to speed up a little bit. We come from a university. We're a relatively young company. Last year, we were able to get funds from the Ministry for Economy and Energy. 1.33 million euros is what we got, and we've planned a pilot run at the beginning of next year together with industry partners. Right, I would like to summarize. As I already said, our measurement system works under any conditions, and it gives you quality measurement precision in a nanometer range. It creates efficiency, and it contributes to cost efficiency and sustainability. Right, on that note, I would like to thank you very much for your attention, and I would love to see you in hall number 6, booth F18. Thank you very much. Wow, Hüseyin, thank you very much. Thank you very much for your timing, because now we still have time for some questions. I have to admit that this is too technical for me, but a great presentation. Thank you. Let's dive in with the first question. Can your system be used in order to detect the wear of machine tools early? Well, yes. Our business model is based on cooperation with OEM partners. That's usually manufacturers of ultra-precision measurement machines, and they integrate them with our clients. There are two options here. We don't test the workpiece when it's integrated in the machine tool, but generally that's possible. The measurement signal and the structure of the measurement signal gives you information on wear, and it can be predicted, and the process can be optimized in order to minimize the wear. What I'm personally interested in with new solutions, new approaches, who's this beneficial for? Well, we currently focus on ultra-precision manufacturing, especially that's processes from the laser material processing, super surface finishings, such as iron beam figuring. But we also had pilot partners with ultra-precision machine tools for working diamonds, for example, where a workpiece stays in the workshop for up to 300 hours, and with an in situ system where they get reliability from the first moment on, and they can use this technology to their benefit. Right, that would have been the next question. Is the use of your technology worth for high precision machine tools? And what is the influence on the throughput and process speed? Well, we have first benchmarks with pilot partners, especially ultra-precision machine tool manufacturers. And for most machine tools, it's the case is that the putting up times of these processes are based on trial and error. So a workpiece is worked, it is tested in the lab, it is worked in the workshop, and then tested in the lab. If we have processes in a sort of vacuum, we have a time of up to 7 hours for setting up that vacuum and in order to assess a process. So the setup time there would take 3 to 4 days. And that is a process that we can decrease to a few minutes. Now, if we look at measurement technologies, and AI, of course, is a buzzword here, do you use AI? And in how far do you use AI? And can that be used in order to get automated measurement results? Well, we are not an AI institute. We don't have an AI background, and that is why I came up with this very technical presentation. The background here is real technology, and this is not data, something funny we're doing with data. Well, AI can be used for predictive maintenance and process optimization for the post-working of measurement data and to render them useful for the machine feedback. Yeah, that would be the biggest use, using your data in order to improve in the future. Right, we have exceeded out the time left. Thank you very much. Give him a big hand. And go visit him in the startup area.